So I want to welcome you to another exciting statistical topic. And of course, the topic today is going to be sufficiency as a property of an estimator. Of course, before now, I've walked you through the properties of a good estimator. We started with the unbiasedness property, to efficiency, to consistency, and finally, today, to sufficiency. So sufficiency is another property of a good estimator. All what we've been doing is just to ensure that the estimator we've chosen is great. And the beauty of statistics, we got a way to investigate that. Now, I want to go into sufficiency now. You to be focused. Now, if I want to talk about sufficiency, okay, this is the idea. If I want to figure out the value of a parameter, I told you the other time, we want to figure out the values of a parameter. The parameter could be mean, variance, standard deviation, could be proportion, it could be difference of means, it could be difference of proportion. It could even be, it could be an unknown parameter in a particular probability distribution. But let me tell you this, whenever we want to figure out the values of a parameter, we normally have a suggestion about what method, what formula to be used. And at times, we could have more than one method, we could have more than one formula. The method and the formula is what we call estimator. And how can we prove to the world, what the formula give or what the estimator give is actually makes sense. And that is why we're trying to investigate the property of a good estimator. When I talk about sufficiency, now I need you to listen. If I go into a population, I take a sample size, okay, when we have a suggested estimator, okay, maybe mean, maybe what we want to figure out is the mean. Now, that suggested estimator, if I apply that on the sample, what I'm going to get is just going to be a summarized value, right? You have a set of data, right? And by the time you use your estimator, you're getting a single value. You're getting a summarized value. Now, this is the deal. If I really want to know whether what we got is sufficient, I'm going to say that again. If I really want to investigate whether that statistic, that estimator, that method, that formula that we use is sufficient, what do I mean by that? You know what I mean? It means, okay, what we got using the sample, using the estimator, if it gives us everything that we need about the unknown population parameter value in such a way that no any other combination of random variable that will give a better information. Then with that, we're going to say our statistic is sufficient. Before I go into mathematical display, because I first want to explain what is behind the scene, I'm actually going to use application in Federal Bureau of Investigation, FBI. Okay, if in the particular community, okay, if a crime was reported, if a crime was committed in a particular community, the FBI is not going to interrogate everybody in the community. They don't have resources for that. We take a sample. And if the FBI, if they're giving reports from their, if they finish their investigation, if they close their investigation, what they are telling the world is that the information they got, there is no any other information anywhere that will actually supersede that. That is what I mean by sufficiency, which means if they got information, let's say they arrest some individuals and they were able to unravel, the true picture of reality as regards to the crime, what are they going to tell the world? There is no any other person in that community that will give a better information. Before they can say that, then it means the approach they use is sufficient. Does that make sense now? Now that you know the idea of sufficiency, because the idea of sufficient statistics can actually be used to derive an estimator that is unbiased and has a smaller variance. Now let's come into mathematics now. Now you know what is behind the scene. What I want to do now is to beg you to focus the board, because I'm just going to be telling you the meaning of all of this. Now take a look at this. Suppose the distribution of a random variable. If you take a look at this guy, why do I write it this way? That's a vector. Talking about x1, x2 up to xn. That's what I mean. Because the FBI is not going to interrogate just one person. They're going to interrogate more than one person. Does that make sense? You understand what I mean? Now, and that is determined by parameter theta. The parameter theta is actually the information we are seeking for who committed the crime in this case. That is parameter theta. Okay, now let us now go ahead. That's a very good one. Send me a message for extra credit. Somebody asked about this, because at times a parameter theta could be more than one. Does that make sense? When you talk about normal distribution, how many parameters? Two. There are some distributions that have more than one parameter, which means at times there could be, before the FBI, there could be more than one parameter of interest. Maybe in a particular community, okay, the crime, they have a multiple crime scenes. Having a multiple crime scene does not mean it's going to be the same perpetrator. Does that make sense? So send me a message for extra credit. Now, the theta 2 is a vector, because we could have more than one parameter of interest. Now, let me tell you this. When I choose x1 up to xn, when FBI interrogates the first person to the last person in the sample, of course, they're going to figure out the number of people they're going to interrogate. Now, because the response that is going to be coming from individual interrogated will actually vary, that will follow a particular probability distribution that we call f of s. So the f of s could be discrete, it could be continuous. And that very f of s is going to be a function of that parameter of interest. Every probability distribution is parameterized. Does that make sense? And at times we may not know. Then some of them may be known, some of them may be unknown. Okay, and that was why I said the functional form of f is known. You know the probability distribution of the population, but the theta is unknown. You need information. Does that make sense? Okay, please, I need you to be going with me with analytical mind. Don't just focus on notation, but try to figure out what is behind the notation. You see, the way I'm chipping in at VI now is for you to be able to understand. Okay, now, and that was, if you take a look at the note, I said we will use F to denote a PDF. We will use P to denote a PMF. PDF is the probability density function of a continuous random variable. PMF means a probability mass function of a discrete random variable. Okay, now any question about this slide? Any question about this slide? Go ahead. Exactly. Actually, in some textbook, some of them just use F. But most of statisticians, they will prefer to say, okay, in order not to cause confusion, they're going to say, okay, let's use F for PDF. Let's use P for PMF. But it doesn't really matter. Okay. Now, I want to go to the next slide now. If you take a look at this, in statistical inference in general, we normally observe a realization of that, like in statistical inference, what we do, just like what FBI is going to do, they're going to observe, they're going to interrogate. When they interrogate, okay, they're going to hear from those people they are interrogating, and whatever they get from them, they're going to put it down. Does that make sense? Okay. And what are they? It means they need information from them. They need them to answer a question, right? That was why I said we need to answer some question about theta. Because why am I taking sample? If there is no problem, then we do not need the investigation. It's either there's a problem or we are anticipating there will be a problem, and that will call for investigation. Now, because of that, let me tell you, take a look at this. We're looking for the parameter of interest that is unknown. At times, we could have more than one estimator that are actually competing. Is it, can I get it in that one or is it in the other one? Then we need to detect that. Just like the FBI want to detect who is the culprit behind the crime. Then then we're going to have a good guess. Okay, the very first one is going to come in terms of hypothesis. That is why you are seeing H. Of course, in statistical analysis, you're actually going to have the non-hypothesis, the alternative hypothesis. Our mind can never be empty. There's always going to be something in mind. When something happens, our mind will go to somebody, and that person is going to be a suspect, right? It could be the person or not. But we now need to have a good guess for that. And where can we have a good guess? It's through estimation. And that was why we were having estimator. Estimator is a formula or method that we use in estimation process. And when we talk about estimation process, okay, estimation process is a way to figure out the values of a parameter using sample information. Does that make sense? So go ahead. Oh, you mean whether different distribution always? Exactly. If before what you're trying to say, before we can use any estimator, at least we need to be able to know the probability distribution, right? Yeah, we have a way to investigate that. We're going to start by first figuring out what is the probability distribution. And that was why I said in the first place that we know the probability distribution, but the issue is we don't know the some parameters, because every probability distribution has parameter in them. Does that make sense? And moving forward, we need a value of the parameter. And that parameter is what we're trying to estimate by means of estimator. Okay. Now I needed to take a look at this now. I told you the other time, this is to tell you, that's a vector, right? And parameter of interest, okay, could be more than one. We got some probability distribution that has more than one parameter. At times we could be seeking for more than one information. Does that make sense? But take a look at this. In order for us to want to avoid what I call over parameterization, we expect the number of observation to be more than the numbers of parameters. And that was why I said P less than N. If N is the number of observation, P is going to be the numbers of parameter. In statistical analysis, okay, it is observed that the number of observation should be more than the numbers of parameter. Now take a look at this. I said one might wonder whether it is possible to compress the measurement. Compressing the measurement is to summarize your measurement. What the estimator you are using is a way to summarize the measurement. Okay, now into a low dimensional statistic. You know, you get a lot of data, right? You use a method on that, and that just simplify and give you just single results. Okay, now, but the summarization we're going to do should not affect the quality of the inference about the value of the parameter, because some people may want to argue this out. When I summarize, that will lead to loss of information. You know that, right? Does that make sense? When I summarize, that will lead to what? Loss of information, right? But we acknowledge the fact that there will be loss of information, and that is why we said from the beginning, we're trying to model reality. Model cannot give us exact reality. There's always going to be error, but we want to try as much as possible to minimize error. So which means we got to choose a method, a technique, an estimator that can actually minimize error information loss. Does that make sense? Okay, now take a look at this guy now. I said, in other words, there exists this guy. Okay, you know, why do I say T underscore bar? Okay, because if I have one parameter, the sufficient statistic is going to be 1. Okay, if I have 2 parameters, the number of sufficient statistic is going to be 2. Therefore, what I'm trying to tell the world now, depending on the number of parameter we want to figure out, then we're going to have a corresponding number of sufficient statistic. Now we said that sufficient statistic, where the dimension is that, such that that sufficient statistics carries all the useful information about theta, even though we have summarized, but it possesses all the useful information about what we're looking for. And that is why we say it is sufficient. And that was why we said, if that is so, then the purpose of studying that, okay, then we could discard the raw data. After summarizing it, after getting the result, what are we going to do? We're going to discard the raw measurement. We're not interested in them anymore. Okay, and what are we going to retain? We're actually going to retain the compressed statistic. So, and that compressed statistic, that summarized, statistic, okay, we believe is going to be sufficient, provided, certain things are satisfied, which I'm going to show you now. Okay, so I'm trying to demonstrate that. We got, if you take a look at this guy, that is actually the vector of measurement. I put it into a machine, we compress that, and at the end of the day, that actually generates an output that is a compressed value. That is a summarized value. When you got a set of observation, when you find the mean, maybe I got 50,000 observation. When you find the mean is just going to be just one data point. That's a summary. That's what we mean. Okay. Now, because of that, I'm going to go into sufficient statistic now. Just like what you said, okay? You talk about knowing the probability distribution. You know where we're going to start from. If you don't have the idea of probability distribution, okay, there is nothing you can do. In statistical analysis, it is requires that we first figure out the probability distribution of the population from which a sample of data is going to be drawn. Does that make sense? Now, that the functional form distribution is known, okay, except that there's a parameter in the distribution that is unknown, and that's what we want to figure out. Okay, now we said this guy is actually a sufficient statistic for theta. Now, mathematics is coming in now. How do you think I know it's going to be a sufficient statistic? If I don't want to go mathematical way, okay, I know it's a sufficient statistic, okay, if after getting a compressed value, okay, there is no any other random variable S that will give a better information. But how are we going, or how can we demonstrate that mathematically? That we're going to say if the conditional distribution of the raw measurement given the sufficient statistic is independent of theta. What do I mean by independent of theta? Means, okay, if I have already figured out my sufficient statistic, okay, the distribution of the random variable from such population, if I can derive that, it is my expression now, there is no theta anymore. If there is no theta anymore, then it means I've already gotten the information that I need. But after trying to work that out, simplify that, you see have theta in your expression, then it means your statistic is not sufficient. Now, because of that, okay, and that was why equivalently I said the functional form, you know, that is going to lead us to having a conditional function. Okay, there's a difference between this function and the initial probability distribution. Now, this function is a conditional function now, which means I've already, I have a sufficient statistic T, okay, and I want to derive the conditional distribution of the raw measurement given the compressed a value in name of sufficient statistic. If I can prove that that conditional distribution is independent of theta, then I'm going to conclude that T is sufficient. Does that make sense? Okay, now take a look at this guy now. You know, just like the beautiful question you asked the other time. Can you see me, right? Hello, can you see me? Okay, you know, you asked a very beautiful question the other time that we need to know the distribution. Now, assuming it is binary now. Does that make sense? It could be any distribution. And that was why initially I said we could be working on a PMF or working on a PDF. Does that make sense? Now, we want to start with Bernoulli now. Suppose we observe, you know, in a Bernoulli, just like the example I gave the other time, okay, maybe I want to figure out how many eligible citizens in a country that approve the job the president is doing. The response, you know, is actually going to be dichotomous. It's either they say, oh, I approve it or not, right? And of course, the state space is going to be 0, 1. 0, non-approval, 1, or approval. And that is why you're saying this. You see that? Which means I don't know parameter theta, but I know the state space. I know it's going to be 0, 1, but I don't know the particular one, right? And of course, my xi follow Bernoulli distribution, IID, which means, you know, they are independently and identically distributed. You know, every person that I ask, I believe they are from the same population of interest. Okay, now this is now, you know what we want to do now is a parameter known. We want to figure it out. And we want to figure it out. We want to develop what I call a sufficient statistic for that. Okay, now, and how are we going to know whether the statistic is sufficient? Is what I'm going to show you now. Okay, now take a look at this. The very first thing is to get the likelihood of the Bernoulli distribution. What I mean by likelihood? The likelihood is, you know, when you have a joint, P Okay, only distribution. This is the expression for probability mass function. In a Bernoulli distribution, that's a probability mass function. Now, the very next thing to do here is I'm trying to get the likelihood. The likelihood is obtaining the joint probability mass function. Okay, joint probability mass function, it means I'm going to have a product. That's what we mean by joint. Why am I having product? Because of independence. You remember in probability theory, if A and B are independent, what happened? The probability of the joint occurrence will be equal to the product of the marginal. Does that make sense? That's what we're applying here. Now, if you take a look at this now, okay, this is like having this in n time, okay, and if you take a look at the k here, that k that you see now is going to be summation x. That's going to be summation s, because if I have 1, if I put 1, that is going to be theta raised to the power x1, 1 minus theta raised to the power 1 minus x1, and I plug in 2 and so on like that, multiply in a general form. That's what I'm actually going to have. Now I got k to be summation x. Now, if I get k to be summation x, now what am I going to do? Okay, now this is a formula. I told you the other time we want to get the conditional, right? If you can show that the conditional distribution of the random variable given sufficient statistic is independent of theta, that we can say is sufficient. Now, if you take a look at this guy here is a likelihood that we just did here. Okay, give me 1 second. Let me clean up. Okay, so take a look at this. That is a likelihood, right? That is a likelihood. Now, we need the denominator. If you take a look at the formula here, what is the probability of k? K is like, what is the probability of the sufficient statistic? Oh, how am I going to know the probability of k? I'm going to go by, what is k? Oh my God, k is summation s. Don't forget, x follow Bernoulli. The sum of s follow. Can somebody tell me? If x follow Bernoulli, sum of x, we follow what? Binomial. Oh my God, everybody, send a message to me for extra credit. Let me see. One point. Let me see how many. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I got 15. I'm expecting message from 15 people. Good job. Okay, now k is going to follow binomial, right? Now, if k follow binomial, okay, if you take a look at the formula, take a look at the denominator, okay, when they follow binomial, then I'm actually going to write, that's a binomial formula. Do you see that? That's a binomial formula. The numerator is actually the joint, okay, of the Bernoulli. The denominator is the probability of summation x. Don't forget, summation s equal to k. When s is Bernoulli, the sum of s is going to be binomial. Now, let us now perform an algebraic operation now. Oh my God. This guy here is going to cancel that guy. What do I have left? You see what I have left? Does he have a theta? It doesn't have a theta, right? Because it doesn't have a theta, then it means the statistic that I got is sufficient. What is the statistic? The statistic is summation x. You know what I mean? If I want to figure out how many of Americans approve the job the president is doing, you know what it's telling me? The moment I know the sum of x. What's the sum of x? It's going to be the sum of the responses, 0, 1. Does that make sense? Then I will be able to figure it out. Any question? So mathematically speaking, if the conditional distribution of your raw measurement given the statistic is independent of theta, okay, then you've been able to figure out sufficient statistic. Okay, now let me tell you this. Most of the time, depending on the probability distribution, of the population, we may not be able to go the way we went the other time. It could be complicated. And because of that, Fisher and Neyman, they came together. They actually give us an easy way to figure out sufficient statistic. And you know what they did? I need you to listen now. You know what they did? What they did is this. Any distribution at all, they're going to get a joint. After getting the joint, they want to see whether if they can partition the expression into two separate functions in such a way that there's going to be parameter in one and there's not going to be parameter in the other one. If they can do that, then they have already attained sufficiency. And that is going to be an easy way, which I'm going to show you right now. And that was why I said, in general, it is difficult to verify the definition of sufficient statistic directly. Okay. And what we can do, I want to go back. Now, this is a theorem. What if I ask you to state Fisher-Neyman theorem? Fisher-Neyman theorem of factorization. Oh, factorization. I remember in mathematics, when they asked you to factorize, particularly, you've heard about quadratic equation, right? If you go by factorization method, okay, what are you going to do? You're actually going to have its function at the end of the day. That is why we call this factorization. And you know what? The Fisher and Neyman, what they did is they look at the joint distribution, which is the likelihood, and if they can partition that mathematically into two separate functions, and take a look at the function now into this guy. Oh my God, that guy has a theta, and the other one, HFS, does not have a theta, and this guy here is a likelihood function. If I can actually, okay, split or factorize a complicated likelihood function of a given probability distribution into two separate functions in such a way that one function, okay, have the parameter theta and the other one does not have the parameter theta, okay, then we're actually going to say, that statistic is sufficient. You know what we want to do now? We want to use this method on Bernoulli. We did Bernoulli the other time. We use a different approach, right? Let's use factorization method now. I need you to be focused now. We are back. We are revisiting Bernoulli right now. Let me tell you, this is the deal. Whatever distribution you are given, try to know how to get the likelihood. If you're given continuous probability distribution, okay, you know how to get the likelihood, which is going to be a joint PDF. If you're given discrete, it's going to be joint PMF. Okay, now take a look at this. What am I doing? That's a likelihood, right? For the Bernoulli. Okay, now let us take a look at this. Let's factorize that. We want to factorize that in such a way, one function will be a function of parameter theta, and another one will be and let me tell you, h of s can be a constant function. Oh my God, in this case now, because when I factorize this guy, when I factorize that guy, I'm still going to have that guy. Therefore, automatically, my h of s is going to be 1. Does that make sense? So 1 multiplied by that is still going to give me that. And you know what? The moment I know that to be, the moment I identify the two function, okay, this is the first function. This is the second one. Parameter, the information is in the first function. Now, I'm now going to go back to that first function. You know what I'm going to tell the world? My sufficient statistics is K. And what does K represent? Summation S. Any question? I'm done. Factorization approach by Fisher-Neyman is very, very easy. All we just need to know is how can you actually obtain the likelihood function, the joint PDF or the joint PMF of any given probability distribution. I want to go into another distribution now, this time around, normal. Okay, you know, when you take a look at normal distribution that we also call Gaussian, how many parameters do we have? Mean and variance, right? At times, the two parameters may be unknown. At times, one may be known and the other one may be unknown. Now, I need you to take a look at this example now. You know, when you see this, FNFT, I mean Fisher-Neyman factorization theorem. Does that make sense? Okay, now we got a normal distribution. Okay, but let me tell you this. Sigma square is known, but mean is unknown. And that was why you say theta in the position of the mean. Does that make sense? At times, mean could be known, variance may be unknown. But in this question now, mean is a parameter theta that is unknown, and sigma square is already known. Okay, now what are we going to do? We want to make use of a Neyman or Fisher-Neyman factorization theorem. Okay, we're first going to write the normal distribution. This is a normal distribution. Wherever you see mu, you're going to put theta because it's unknown. Now, if you take a look at this guy, that is trying to get a joint. That's going to be a product. Okay, now, and if you take a look at that, if you apply that, you're actually going to have this. Whenever you want to apply a joint, okay, whenever you see S on the exponent, that S is going to be summation. Do you say summation? Okay, and on the constants, if you take a look at this guy, if I want to rewrite that guy, I'm actually going to write 2 pi, okay, sigma squared. Okay, everything in square root is just going to be, and don't forget, 1 over that is just going to go, if I wanted to go up, it's going to be negative half. And if I want to have this guy over n time, then it's going to be that. It's going to be that guy there. Now, what am I going to do now? There's a lot of work to do. I want to use a factorization theorem on this guy. I want to be able to factorize this into a function, to 2 functions. One which is going to contain theta, and the other one is not going to contain theta. Take a look at this guy. That does not contain theta, no. But every other one here, what happened? There's a theta in that, right? That means you've been able to get that. Now, if I now want to know which one is sufficient statistic, okay, now you actually, the sufficient statistic, don't forget, the focus is on the mean, okay, the sufficient statistic is going to be this guy, summation x. Do you see? Minus 2 theta. You see that? The sufficient statistic is going to be, you're actually going to get the sufficient statistic in the function that contains theta. Does that make sense? Now the sufficient, so which means if I want to figure out the mean, if I know summation s, then I can figure out the mean. And I can, do you know that I can also say x bar? Because summation s, if I simplify this, divide by n, do whatever, so I can say summation s or x bar. Okay, now I'm going to show you another example. What if in a situation where the 2 parameters are unknown? Do you see the reason why theta is a vector the other time? Like in this example now, the 2 parameters are unknown. We don't know the mean, we're going to know the variance. What are we going to do? You need to get the joint, you're going to get the likelihood again, and you're going to see the entire expression is going to have theta in them. Because of the theta 2 there, you understand what I mean? Which means the entire expression, this guy here is going to be the g of theta, and 1 in a case of a situation where the 2 parameters are unknown. Now, if the 2 parameters are unknown, what am I going to do? There's going to be two sufficient statistics. That was why the other time this was having that's also going to be a vector depending on the numbers of parameter. Now, if I really want to know, take a look at this guy. Okay, theta 1, then what multiply that, the summation S is going to be a sufficient statistic for theta 1. What about for theta 2? If you take a look at this guy here, you know it's also multiplying this, right? Then summation S squared is a sufficient statistic for variance. Don't forget, if you want to find variance, okay, the summation S squared. You're going to consider summation S squared because if you take a look at the formula for variance, let me show you this. The sample variance is summation, okay, x minus x bar, okay, all squared divided by n minus 1. Do you know I can expand this guy, the numerator? The numerator can be summation S squared minus summation x all squared divided by n, then everything divided by n minus 1. So that's another expression for sample variance. And that is why if I want to get the sample variance, then I need summation S squared. So finally here, the statistic now is going to be a vector. Take a look at this. Summation x for theta 1, summation S squared for theta 2. The theta 1 is the mean, the theta 2 is the variance. Okay, these are okay. And if you don't want to say summation S and summation S squared, instead of summation S, I can say X bar. Okay, I can also say this X bar, or I simply say sample variance. Does that make sense? Sample variance for population variance. Okay, now I think I put an example here. This is in the textbook, and I gave my TA I think I gave him some problem to work on this week in the lab. Now take a look at this question here. If the first question is you are talking about normal distribution, okay, with mean, mu, and variance. If mu is unknown and sigma square is known, show that y bar is. I just showed that today. I just show you. Okay. Now the second, if mu is known and sigma square is unknown, show that that is sufficient. You can try that. What if both are unknown? That's what I just showed you now. Show that the summation y and summation y squared will be sufficient. Is another question? You're given a Poisson, you can be given any distribution. You're given a Poisson distribution, show that summation y is sufficient for lambda. Lambda is a parameter in Poisson. 940. If y1 up to yn follow Rayleigh distribution, that's another distribution continuous in statistics. So show that summation y squared is sufficient for theta. I will advise you follow the Fisher-Neyman factorization theorem. Oh my God, that is looking like, okay, this is another one. You were given that exponential distribution. Show that y1, what is y1? Minimum statistics is sufficient for theta. Like I said, my TA is going to walk you through some problems. This is where I'm going to stop today. Is there any question? Is there any question? Do you now understand how sufficiency work, right? Whether mathematically speaking or go ahead. Yeah, actually, yeah, that is the idea. We're looking for parameter theta, and we four of us get the underlying distribution. It could be any distribution. So which means what are we advised that you should start doing now? How do I get likelihood function for every distribution? If then it will be very easy for me to use a factorization theorem given by Fisher and Neyman if I can split that into two mathematically in such a way that one function will have a theta and the other function will not have. Let me tell you this. When I was studying this in Africa, I was like, practically, what is it meaning? Oh, when a crime is committed in a population, when FBI interrogates some people and they don't interrogate some people, the people they don't interrogate, they don't have the information. No, see that here. The people they interrogate ask the information. That is it. Okay, you're welcome. Okay, make sure you stay safe and have a lovely day. Bye for now, everyone.